All right, today we're jumping into the world of some seriously generous chemical donors. We're talking about polyprotic acids. These are the ones that can give away not just one, but multiple protons. And to kick things off, let me ask you something. You ever take a sip of soda and wonder, what is that? That sharp, tingly, acidic bite? Well, the answer to that is actually the perfect way to understand exactly what we're talking about today. Okay, so to really wrap our heads around this, we've got to start with the basics. We need to look at the difference between an acid that gives away just one proton and one that gives away a bunch. It's kind of like a tale of two very different acids.
Now, you're probably familiar with the simplest kind of acid, right? A monoprotic acid. I mean, the name says it all. Mono for one. These guys have exactly one proton to give away. Think of something like hydrochloric acid. It donates its proton and bam, its job is done. Super simple, super straightforward.
So let's put these two side by side for a second. On one hand, you've got your monoprotic acids. They donate one proton. One step, that's it. But then you have polyprotic acids. Poly, of course, meaning many. They donate more than one proton. And this is the really important part. They do it in multiple steps. And that soda we were talking about, the carbonic acid in it is the perfect example. And that whole multi-step thing? Yeah, that's the key to understanding all of this. See, polyprotic acids don't just, dump all their protons out at once. No way. It's a much more controlled step-by-step donation. This process actually has a name. It's called stepwise ionization. The acid molecule lets go of its first proton. Then the thing that's left over, which is now an ion, might let go of a second one. And you get the idea. Every single donation is its own separate event, its own little reaction. Let's walk through it with a generic example. We'll call it H2A. So in step one, the neutral molecule gives up a proton. And what's left is a negative ion, HA-. Okay, simple enough. But then in step two, that negative ion gives up the second proton, and it becomes even more negative, A2-. See? It's a two-stage release. And this right here reveals the golden rule of polyprotic acids. I mean, think about it. It's just much, much easier to pull the first proton away from a neutral molecule. But trying to pull a second positive proton away from an ion that's already negative, that's way tougher. The attraction is just stronger. And that's why the first donation is always, always the strongest one. Okay, let's circle back to our can of soda. Because now we can actually look at the carbonic acid inside it as a perfect case study for this whole stepwise thing. So you know that fizz, right? That's just carbon dioxide gas dissolved in water. And when CO2 meets water, they react and form H2CO3, carbonic acid. Now this is what we call a weak diprotic acid. Diprotic just means it has two protons it can donate. And being weak means it does so pretty reluctantly. And this is where that rule we just learned really comes to life. Just look at the data here. The first step, where carbonic acid turns into bicarbonate, has an ionization constant, a Ka value, of 4.3 times 10 to the minus 7. But then look at the second step. Bicarbonate becoming carbonate, the Ka drops all the way to 4.7 times 10 to the minus 11. I mean, those numbers aren't even in the same ballpark. They're worlds apart. Just how far apart are we talking? Well, that first proton donation, it's about 10,000 times stronger than the second one. 10,000. It's just so much easier for the acid to get that first step done. The second donation is just a tiny, almost insignificant fraction of the whole process. All right, so if you're a chem student, you might be looking at all these steps and thinking, oh no, the math for this is going to be a total nightmare. And honestly, it looks that way. But that huge difference in strength we just saw, that's actually the key. It's like a secret shortcut for chemists. Yeah, at first glance, trying to solve for all the different things floating around in there, it seems crazy complicated. You've got the original acid, you've got two different kinds of ions, plus all the protons. It really does sound like a total mess. But here's the beautiful aha moment. Because that first step is so much stronger than the second one, we can pretty much just ignore the second step when we're trying to figure out the acidity. It lets us treat each step separately, which makes the math, so much simpler. So what's the bottom line from this shortcut? Well, for a weak acid, like our carbonic acid, a couple of things are basically always true. First, nearly all of the acidity, all those H+ ions, they come from that first step. The second step barely contributes at all. And second, and this is a really cool little trick, the concentration of that final ion, the CO3 2-, turns out to be pretty much exactly equal to the value of that second constant, Ka2. How neat is that? And what's really cool is that this beautiful, simplifying pattern, it isn't just some one-off trick that only works for carbonic acid. Nope, it's a universal principle. It works for acids that have even more protons, and it even works for bases too. So you can probably guess what a triprotic acid is, right? Tri for 3. It has 3 protons to donate. And guess what? It follows the exact same pattern. It gives them up one by one, and each step is way, way weaker than the one that came before it. Just take a look at phosphoric acid. Its first Ka is around 10 to the negative 3. The second one drops all the way down to 10 to the negative 8. That's 100,000 times weaker. And the third one? It absolutely plummets to 10 to the negative 13. The pattern doesn't just hold, it gets even more dramatic. And just to blow your mind a little bit more, this isn't just a story about acids. The exact same logic works in reverse for polyprotic bases, things that accept protons. They do it in steps too, and every proton they take on makes it that much harder to grab the next one. It's this really beautiful fundamental symmetry you see in acid-base chemistry. So, when you think about it, from this simple fizz in your soda all the way to incredibly complex systems inside our own bodies, this stepwise process is happening everywhere. It really makes you wonder, doesn't it? If something as basic as an acid gives up its protons in this elegant, ordered little dance, what other amazing, complex chemical ballets are happening all around us all the time, just waiting for us to figure them out?